Good morning. This is going to be the second part of the rotational equilibrium video. So this is basically the answers, how things are done. All right, so I'm going to start with actually pages 13 and 14. Page 13 we'll do in class, we'll do it together. Page 14 we'll probably do in class, I'll have you do it. So I'm going to jump right on page 15. It says a uniform steel beam has a mass of 1,000 kilograms, so basically it's this beam. On it is resting half of an identical beam, so it's right here as shown. What is the vertical support force at each end? So I think what we should do here is say, well, you know what? There is a support force from here, so I'll call it F1. There is a support from here, it's F2. And we can probably see conceptually that F1 is going to be larger than F2 because it has to support more of the weight. So let's say if the math confirms that. And we also have this mg, and we have half mg here. So I'm going to start with the net torque equals 0, meaning like it's balanced rotationally. So I'm going to pick just one point. I don't care. So I'll just pick this point here as the axis of rotation, as the pivot point. So let's see. So F2 gives me a counterclockwise torque. So it's going to be F2. How far is it from the axis of rotation? L equals these two forces, okay, with respect to this axis of rotation that's coming at us will give me a clockwise torque. So it's going to be mg L over 2. That's how far this is from here, plus 1/2 mg, and this is half of half, so this distance here, so it's a quarter, so L over 4. So now we can cross things out. We can also cross out the mass and, oh, no, we can't cross out the mass and the g, sorry, because there's no g here. So F2 is just going to be, so let's clean this up. Mg over 2 plus mg over 8, which is equal to, if we make that an 8, we make this a 4, so it's 5/8 mg, and I did the math earlier, so it's 5/8 of 1,000 times 10, so 6,250 newtons. Now to do the other one, to do F2, to do F1, we can change the pivot point to F2, to where F2 is. But if you don't want to do that, we can just do forces up equals forces down. In other words, F net, or net force, equal to 0. So F1 plus F2 equals half of mg plus mg. So F2 we already have, and this looks like it's 3/2 of mg, which is 1,000 times 10, and F1 should be 8,750 newtons, and we expected F1 to be larger earlier conceptually. All right, let's look at number 16. A 70 kilogram adult sits at one end of a 10 meters board, right? So here's the board. So here you basically have the 70 kilograms right here, okay? On the other end of which sits his 30 kilogram child. So the kid is sitting here, okay? And so basically, I guess we can call this M father times G, and this is M child times G. Those are the forces. And here it says, it doesn't say anything about the board, so we're going to ignore the mass of the board. Okay. Now it says, where should the pivot be placed so that the board is balanced? So we're looking for where to put that fulcrum. So if I put it here, let's just say closer to the kid, right? It's a short distance and a small force, so I don't think it makes sense, compared to a large force, right, and a large distance. So this torque here will be dominating. So it should be, logically speaking, it should be closer to the father, right? So I'm just going to make sure that I did this the same way. Okay, so I think I called this here x. Yeah, that's what I did. Okay, so if that's x, this is going to be 10 minus x. Now, if this is balanced, it means the torque caused by this mg has to be equal to the torque caused by this mg. So if we have to write this, it will be mfg times x equals mcg times 10 minus x. And I think the g's can cross out. And if we do the math correctly here, we should get x equals 3 meters. Now that's from the adult, from the father, I guess. Okay? All right. Okay. Let's do the same one, but this time we have to take into account the mass of the board. So the force, the weight of the board is right smack in the middle. So this is going to be, I'll just call it mg, or m board g. So let's see what we can add to this equation here. Now, I think we can figure out this distance here, because from here to here is 5. And if this is x, this should be 5 minus x. So let's see what's going to change. Okay. You know, I'll start all over. Okay. So this is going to be m father g times x equals the torque caused on this side here. So m child times g times 10 minus x plus mbg times 5 minus x. All right, so I think we can get rid of these g's. So this is 70 times x equals 30 times 10 minus x. I could have probably made this 300 minus 30x. Okay, plus the mass of the board is 15, so it's going to be 15 times 5, which is 75 minus 15x. So let's see what we can do here quickly. So if I put this 30, and so that's going to be 115x, it looks like, equals 375. So x equals so 375 divided by 115. It should be 326 meters. Again, still from the father. Okay. All right, let's look at the next question. Okay, we are on number 18. So this dot here, that's basically your pivot point. Okay, find the net torque here. So this is not, we don't know if it's in equilibrium or not, so we just have to find the net torque. Okay, so you can see that F2 gives you a counterclockwise torque. So the net torque is counterclockwise minus clockwise. Okay, so this is going to be F2 times, well, how far is F2 from this pivot point? So I guess it's going to be the difference between 10.5 and 4.8, which I don't want to do, so I'm just going to look at it. It's 5.7. So this distance here is 5.7 meters. Okay? Minus the torque caused by the clockwise. So F3 is pointing down, so it's going to make it spin this way. So that's 60 times 10.5. And if we do the math correctly here, it's negative 202.5 newtons times meters. So this is negative, which means it's going to go counterclockwise. And if you don't want to put the negative there, you can just say 2, 2.5, counterclockwise. I'll leave that up to you. Okay. All right, let's look at number 19. So the pivot point is here, so that's the dot there. So sometimes it's an X, sometimes it's a triangle. If the object below is in rotational equilibrium, solve for the missing force. So here so I think in the packet, I think I told you to cross out the 350. If I haven't done that, just cross it out. So we have to find out what that force is. It's not going to be 350. Okay. So I think we can figure out this distance here. Okay. Okay, which is going to be that distance. I don't have it, but I think we can figure it out. So if this is 25, and so let's do this. Okay. So if this is 25 and this is 18, I think we're left with a 7 here, and this is 5.5. So this is 12.5. Okay, I think it should be 12.5, right? So 25, take away 18, and you add 5.5. Yeah, I think it's right. And if that's 12.5, this is also 12.5. I don't know if we're going to need that, but just fill in the blanks here. And this distance here should be 7. Okay. So if it's in the rotational equilibrium, let's start with the net torque V in 0. Okay. Which means, let's look at the forces that give me counterclockwise with respect to this point here. I think it looks like F2 will go spinning this way. F1 will also do the same, right? Yeah. Okay. And F3 will go clockwise. Now, F4 will not generate any torque because it's acting right at the pivot point. So let's see what we can do here. So we say this 2 will give me counterclockwise. Okay, so F1. Okay, actually I'll just go right for the numbers. So it's 200 times, how far is this from at the end? 25 meters plus F2, which is unknown. Yeah, we're looking for that. F2 times 12.5 should equal to the clockwise torque. So F3 times 7. Okay, so here we have 2 unknowns. So I think what we should do here is just rely on the F net equals 0, okay, because you are balanced up and down, you're not moving up and down. So it's static equilibrium both for rotation and for translation. Okay, so it should be F3 equals F1 plus F2 plus F4. You cannot ignore the F4 there. So let me see what I got here as an answer. I don't think I have it. Actually, okay. So I think let's plug in some numbers here, and then I'll show you what to do. So this F4 is 250. Okay. F1 is 200. Okay, that's what I think I have. Yeah. Yep. So I think if you set this up and you do a system of equations, you should be able to figure it out. So maybe just move the F2s and the F3s to one side, do elimination or do substitution. But at the end, you should get F2 is equal to negative 336.2 36 newtons, and F3. So which means that the drawing is not correct, which means F2 should be pointing up. Okay? Yeah, that's what that's what it should mean. F3 is 113.64 newtons. So you just have to solve this system, and I really don't care how you do it. You can do matrices, whatever, it just doesn't matter. You can do elimination, substitution, just do it. Okay. Okay, so 20 and 21 we're going to answer together. So so you have an ant here, so we're trying to figure out what position is going to be hard for it to stick to the wheel. So logically speaking, I think it should be 3. Okay, and here is why. So when it's at the bottom here, there is mg, okay, and there is a force, okay. There's a force here from the ant. So it should, if you do the centripetal force stuff, it should be F minus mg equals m r omega square, or mv square over r. So F is going to be equal to mg plus something. Okay? So which means the maximum force is going to be down here at the bottom. It's mg plus something else. So it should be a part at location 3. And I think we can answer this one too. So what is the magnitude of the minimum force? So it's just mg plus mr omega square, and we just answer both questions. Okay. All right, in the first part of part 1 of the video, I did an example like number 22, but it was a little more challenging than this actually. Okay, so this should be easier. Okay, as shown, a 10-meter long body is attached by a frictionless hinge right here, okay, to a wall and held horizontal by a light rope that makes an angle 49 degrees with the bar. The bar is uniform and weighs 66.5. Okay, so we have to figure out where to put this mass here, okay, so that the tension is 177. So here's my tension. Okay, so here I have to put this mg for this weight here, which is basically 100 newtons, right? And we have to do the mg for the bar. So I really don't know where the middle of the bar is, so I'm just gonna guess that it's there. Okay, and I think it tells us the bar weighs 66.5 newtons. And the angle is 49. Let me just label everything. And we want this to be 177 newtons. Okay. So let's do torque here, right? Torque with respect to this point here. Okay, so let's figure out which one gives me counterclockwise torque. It looks like T, or at least this vertical component of T gives me the counterclockwise. So it should be T times this length here. I'll just go for the numbers. It's 177 times 10 sine of 49. Okay. Now, these two mg's, they want to make you go clockwise. So that should be equal to, because this is in equilibrium, so net torque is 0, or counterclockwise equals clockwise. So it should be equal to 100 times x plus 66.5 times the length. This is 10 meters, so times 5. Okay, and if you do the math here, you should get 10 meters. So basically you have to put this all the way at the end here. I think in the answer it will come up to be like 10.03 or something like that, but that's about 10. Okay, so you round it. This problem here I did in the part 1 video, so you can just go back to part 1 and see how I did that one. Okay. Now we're going to try to do the RT8 fishing rod, weight of 2 pieces. Okay. So you have that's balance. So if we cut it here, okay, would the weight of the piece on the left hand side be greater than, less than, or equal to? Okay. Now, this distance is very short, right? In here, the center of this is somewhere in here, right? Okay. Center of this whole thing is somewhere in here. So this is kind of like longer, whatever that center is. Okay. So if this is long, in order to balance, you don't need a lot of force, and this is lighter. Okay. And this side here is heavier, right? Because it's closer. So this has to be heavier. You have to have a bigger mass here. Okay? So greater, it should be greater than. Okay? Because here, the trick here is that you're tempted to say that they are equal. Yeah, the torques are equal, but not the forces that generate these torques. In other words, not the weights. Okay, so the weight of this is here, and the weight of this is here. This distance is larger than this distance, which means this has to compensate, okay, by being larger so that the torques are equal. Okay. So the mass here is the same. A downward, oops. Okay. A downward force F keeps the rod at rest. The rod in case A is 50 centimeters long, and the rod in case B is 40 centimeters long. So I don't think it matters because the point of application is only like 3 dashes away from the fulcrum in both cases, right? So I don't think we care about that. Each rod is marked at 10 centimeter intervals, right? Will the magnitude of the vertical force F exerted on the rod be greater in case A, greater in case B, or the same? All right, so let's see. So the torque here is basically just, I call this L, so it's FL, because the angle is 90. So let's look at it here, okay? So this force is acting down this way, so the angle between, okay. So if I call this angle here theta, okay, I can probably prove to you that if that's theta, I can prove to you that this is also theta, right? Yeah, it should be, right? Because these two lines are parallel, so these angles in red are congruent, right? So which means this is also theta, same as that. Okay. So the torque here, well, this is the torque here is just 2,000 times. I guess I'll make this 3L. I'll make this L times L. This here is, yeah, okay. In here, the torque by this one is what? Okay, well, let's just look at the torque by this. So it's going to be F times L sine of theta. And that should equal the torque caused by this one here. Okay, so this is 3L here, because 1, 2, 3. And this is going to be 200 times 10 times G sine of theta, because that's the angle between the force and the lever arm on this side. So I don't think the angle matters actually, right? So we end up with the same thing, right? And there is an L here. this L here, right? So those two are equal. So we pretty much ended up with the same equation. So the force can be the same, or should be the same. For RT10, we have to answer these questions based on these different scenarios that can happen. Okay, so it's basically saying, so we have to choose from here, from these 5 choices. The 100 Newton weight is moved to a position closer to the pin. So if we move this closer here, right, and you want to keep the same torque, and we want to keep the force at the same place, so we're not moving the force. So this is going to generate, this 100 newtons will generate less torque, so we don't need as much torque as we have now. So I think we can lower the force F. Okay. The next question, the support force F is moved to a position closer to the pin. So F comes here. So now we sacrifice distance, or the lever arm, so we better get that F higher so that to maintain the same torque. So that should be first choice. Now part C, the weight is decreased to 50 newtons. So if we decrease this to 50, so we're generating half the torque, so which means we have to cut this force here by half for the balance to stay the same. You want the torques to be equal. So half the torque here, then you should only have half of what you have on the other side. So that should be option 2, to decrease the magnitude of the force. The support force F is moved to the right end of the board. I think we did that. Oh, it's moved to the right. So if you increase this distance, now you have a longer arm, which means you need a lower force. So you have to decrease F here, because for a constant torque, force and the lever arm are inversely proportional. The board is made longer, but the support force remains at the same location. Yeah, I don't think that matters, because what we're measuring here is the distance from the point of application of the force to the pivot point, to the fulcrum. So that should have no effect. That's option 4. And the last one is the 100 Newton weight and the support force F are both moved to positions closer to the pin. I don't think we can tell here, because it just says it moved closer, so we don't know where they're going to be moved. So cannot tell. Okay, so that's option 5. Okay. Okay, let's look at number 24. So you have a platform here. So you have 2 chains, 2 cables. They are a meter away from the edges, from the ends. The scaffold itself is 25 newtons, which means 2.5 kilograms. And that's too little for a scaffold. So this is 25 newtons. Okay, I'm going to label this as tension. I'm going to just be consistent with what I did. So I label this as tension 2, and the tension here is tension 1. Okay. The window washer is located 1 meter from one of the chains. Okay, so I put the window washer closer to here. And a bucket is 1/2 meter from the opposite chain. So here's your bucket here. Okay. Oh. Okay. Okay. So I think his guy is 1 meter away. This is 1/2 meter away from the edge. find the force in each of the chains. So I'm just going to be consistent with what you have in the answer key. So I'm going to pick this as my pivot point. So I have to figure out the distances from each one of these forces, because now you have 1,000 newtons weight from this guy, and you have 5 newtons from the bucket. So I have to figure out the distance from the point of application of these forces to the axis of rotation. So this is 0.5. From the center here to the end is, okay, the whole thing is 5 meters. So this whole thing is 5 meters. Okay, so from here to here is 2.5, which means from this position to this position here, it should be 1.5 meters. Okay, because you have to leave 1 meter on the other side. All right. Here we're losing 1 meter. I'm talking about this guy. We're losing 1 meter here, 1 meter here. That's 2 meters. And we're losing 1 meter here. So that's 3 meters. So this person is going to be 2 meters from the other cable. Okay, so now let's do the math. Okay, the T2 is going to give you clockwise torque, and I think all these other 3 guys will give you counterclockwise. So counterclockwise torque, counterclockwise should be equal to clockwise. So the counterclockwise torque is going to be 1,000 times 2 plus 25 times 1.5 plus 5 times half, and that should equal the clockwise torque, which is caused by T2. So it's T2. Now how far is T2 from T1? I think it's 3 meters. So T2 is going to be equal to 680 newtons, right? Now to find T1, we just do F net equals 0, because it's in a linear equilibrium or a translational equilibrium. So T1 plus T2 is equal to 1,000 plus the 25 plus the 5, right? And you should get a T1 that's equal to 350 newtons, and which actually makes sense. T2 has to be larger because it's supporting more. I mean, the heavier person is closer to it, so it makes sense. Okay, 2 pillars at the end of a bridge support a 6,000 Newton bridge. So here's your bridge. Supports are all the way at the end. So they're giving you 2 forces, F1 and F2. Let me just make sure I'm consistent with what I did here. Yeah, F2 is on the right, F1 is on the left. The bridge is 50 meters long, and a 1,000 Newton car is parked 5 meters from one end. So in here I put the car on the right here. So the car is here. Okay, and this distance here is 5 meters. This whole distance here is 50 meters. Okay, I'm trying to find the force on each support. So first thing I want to do is I want to do the weight of the support itself. I mean, or the weight of the bridge, which is 6,000 newtons. The weight of this car. So now here you can see that F2 has to be greater than F1 because it has to support more. And the car is 1,000 newtons. So, so I'll pick, in my notes I picked this point here as my pivot point, right? That's what your axis of rotation is. So I'm going to say the counterclockwise torques, which is caused by the 6,000 times, now that's going to be no, it's going to be 25 meters away because this is acting at the center of mass. plus 1,000 times 5 equals clockwise torque caused by F1. So F1 times 50. And if you do the math correctly here, you should get F1 equals 3,100 newtons. And then if we just do F1 plus F2 equals 6,000 plus 1,000, 6,000 plus 1,000. And if we plug in F1 as 3,100, we should get F2 equals 3,900 newtons. Okay? And we kind of predicted that F2 has to be larger because it has to support more. Okay, two strings, one at the 5 centimeter and the other at the 93 centimeter support and 1 Newton meter stick. So here's your stick. Okay, here's your 0 mark. Here's your 100 centimeter mark. So the support is, one is, I guess we can call this tension. I call it tension 1. The other one is tension 2. I'm going to try to do this and keep everything in centimeters because it's all proportional. So because there is equilibrium here, so it's all proportional. As long as you keep everything in centimeters or everything in and everything in grams, you should be okay. Okay. Now, if you have to find the net torque, you have to change everything to meters and kilograms. So this is my T2. Okay. So this distance here is 5 centimeters. This distance here is 7 centimeters because you are at the 93 centimeter mark from the 100, and the stick itself is 1 Newton. So from the center of it is 1 Newton. A 5 kilogram mass is hung at the 35 centimeter mark. So 35, let's just say it's about here, right? So we're going to hang something here, okay, on the stick. So this is going to be 5 newtons. All right, so maybe we can figure out what this distance is here. So I think this is going to be 30. I don't know if we're going to need it or not, but it's fine. If we need it, we'll use it. Okay, find the force of tension in each string. So I think I used, what did I use? I think I used T2 as the pivot point. So I think this time I'll just change it. I'll just make it T1. Why not? Yeah. All right. So I'm going to do the clockwise torque equals counterclockwise. So let's see which ones cause counterclockwise. It looks like these two weights will give you a clockwise, and the T2 will give you counterclockwise. So counterclockwise equals clockwise. So T2 times, now how far is T2 from T1? Well, it's 100 centimeters minus 12 centimeters, so that should be just 88. And I'm going to leave it in centimeters. Equals 5 newtons, and that's 30 centimeters from here, plus 1 Newton times, now this is at the 50 centimeter mark, so that should be 45, because you have to take away this 5 here. So let's see what T2 is. Yeah, in the answer key I did it differently. So that should be 195 divided by 88. Should be 2.22, and that's what I had. Newtons, right? And you can just say that T1 plus T2 equals 5 plus 1, and you can get your T1 to be 3.78. That's using F net equals MA. Right? See, all these problems are pretty straightforward. So I think I'm gonna just, I'm just gonna skip here a little bit. So I'm gonna go to number 29, because they're pretty similar. Okay. Okay, so 29. Sam weighs 400 newtons and sits at the end of a 2-meter long seesaw, right? So I think I put Sam on the left side. So this is 400 Newton force. So this whole thing is 2 meters. If the pivot point is 0.65 meters from Sam, so here's the pivot point, and this distance here is 0.65 meters. And Sam's friend Yams sits at the other end. So we're trying to figure out her weight. Okay. So this is the fulcrum basically, right? So we can say that Sam generates a counterclockwise torque. So 400 times 0.65 equals, I guess, the mg for Yams times, well, how far is she from here? It looks like she is 1.35 meters away. So this force here, or this mg, is going to be 192.59 newtons, right? Okay. So now we know that this force here is 192.59 newtons. So which means 19 kilograms. Pretty light girl. Okay. Based on the information in problem 29 and its solution, suppose a 225 Newton child sits 0.2 from Sam. So let's try it again. Okay. So now you have a child that's here, and this distance here is 0.2 meters. And the weight of the child is 225 newtons. Where must a 325 Newton child sit to maintain rotational equilibrium? So I call this distance here x, and I'm going to put that child here. So that's 325. So we just have to do equilibrium again, right? So the torque caused by these two guys has to be equal to the torque caused by those two. So in here it's going to be 400 times 0.65 plus 225 times, I think you can see that this is 0.45 equals, let's look at the torque caused by this. So it's 325 times this distance that I called x plus 192.59 times, what is that? I think I could have done it much quicker than this, but that's fine, it's too late. So this is going to be 135. Okay, and if we do the math correctly here, we should get x equals 0.312 meters, or 31.2 meters from the fulcrum. So you have to specify that from the pivot point. All right, let's look at 31. A uniform meter stick supported at the 30 centimeter mark. So here's your meter stick, here's your 0, here's your 100. Okay, it's supported at the 30. So this is your 30 centimeter mark. Okay. Is balanced when a 0.5 Newton weight is hung at the 0 centimeter mark. So 0.5 newtons here. Okay. What is the weight of the meter stick? Now, the weight of the mirror stick, or the force of gravity on the mirror stick, acts at the center of the mirror stick. So that's going to be your mg. All right, so with respect to this point here, the 0.5 newtons will give you some counterclockwise torque, and the mg will give you clockwise torque. So these two have to be equal in order for this stick to balance. So it should be 0.5. Okay, well, here they're looking for the weight. So I'm just going to call it Fg, I guess. 0.5 times. Now, how far are we here? It looks like we are 30 centimeters away. I can leave everything in centimeters as long as the object is not rotated, right? As long as the torque, the net torque is 0. Equals Fg times, well, how far are we here? It looks like it's 20 centimeters. So this is going to be 0.5 times 3 over 2, which is what? 1.5. So that should be 0.75 newtons. Yep. Now, if we need to figure out the mass, it will just be 0.075 kilograms, which is 75 grams. I think I'm going to skip again, and I'm just going to jump right to number 35. This is a little bit more challenging. A uniform ladder of mass m. Let me just make sure we're still recording here. All right, we're good. Okay. A uniform ladder of mass m and length L leans at an angle theta against a frictionless wall. So there is no friction here, as shown. If the coefficient of static friction between the ladder and the ground is mu, what is the minimum angle at which the ladder will not slip in terms of mu? Oops, forgot a parenthesis. Okay. All right, so just going to try to do this as 1, 2, 3, 4. Just do it here. Okay, so this is the mass of the ladder times g. Okay, there's the force of static friction here, because you don't want it sliding that way. There's a normal force, that's a support from the ground, and the wall is kind of like pushing this way on the ladder. So F, I guess I can call it F wall. Okay. All right, so I'm going to pick this point here as my pivot point. I think in the answer key, I think I picked this point up here as the pivot point, which I think made things a little bit too long. So I'm going to choose this point here, because if I choose this point here, I can get rid of two forces. Neither one of these two forces will generate any torque. So let's try this. So we're going to spin around here, right? So this force here will make you go, will try to make you go counterclockwise, and the mg will try to make you go clockwise. I hope you can see that, right? But the other thing we should notice here is that we should be balanced both horizontally and vertically, right? Which means this F, the push of the wall or the support of the wall, okay, should be equal to the force of static friction. And this normal force here, okay, should be equal to mg. Okay, forces up must equal forces down. So that's what my picture should look like now. All right, so let's try this. So I'm going to do the counterclockwise torque equals the clockwise torque. I don't want this thing slipping. So the counterclockwise torque is caused by this F here, this force of friction. Now I'm going to try to figure out, I'm going to do that R perpendicular idea. I'm not going to do FR sine theta. So I'm going to try to figure out how far is this line of force here from the axis of rotation, right? And if you look at it closely, that thing is just L sine theta. I hope you can see that inside this triangle. That distance is the same as this distance here, okay? So that's going to be F L sine theta, okay? Now, the mg here, okay, I can do it this way. I can say, you know what? I'm going to extend this line, okay? And I'm just going to find the shortest distance between that line of force and the axis of rotation, which is right here, okay? Now, this whole thing should be L cosine theta, right? Inside that triangle. Okay, if this is uniform and the mg is acting at the middle here, this distance here should be half of L cosine theta. All right, hope we can see that. Okay, so it's going to be mg, what did I say? L cosine theta over 2. Okay, so now I think we can say that the force of friction is mu times Fn. And Fn, we just talked about it earlier, is just mg in this case, right? So I think we can just start crossing things out. Okay, so let's see what's left. Let's clean this up a little bit. I can see that mu sine theta equals cosine theta over 2. So so we're looking for the angle here, right? So I'm going to say sine theta divided by cosine theta is going to be equal to 1 over 2 mu, right? Well, this is just tangent of theta here. So which means theta is just the inverse tangent of 1 over 2 mu, okay? And that should do it for this part of rotational equilibrium. All right, have a nice day. All right, I'm out. Peace.